Hi, my name's Erin Clark.
And I'm Ben Weaver, and this is Lab 2, Gaussian Beam Profiling and Propagation.
So for the first part of the lab, we were using the knife edge test to find the beam profile. To begin this test, we started by putting the microscope in our optical rail and then determining where the surface of our laser aperture was in order to get A0 for our new reference axis. And then we moved that an arbitrary distance away. We chose 1,000 millimeters. And then we placed our knife edge at the position where we saw the focus in our microscope. For the next part of this lab, we were able to profile the beam by using this knife edge right here. We started at a position where the beam was not hitting the knife edge, and then we were able to move the knife edge across the beam. And by using our TIA, we were able to see the changes in power, which will enable us to analyze the beam further. We also need to perform the knife edge test at a second location. This allows us to determine the beam radius at 2 different locations. We can then use the Gaussian beam profiling algorithms to find the beam waist, its location, and the Rayleigh range.
So in the second portion of the lab, our aim was to solve for the size of the secondary beam waist. So what we did was induce a lens right here, and we make sure that it was aligned using the same method that we did in the previous lab, which was taking advantage of the 4 degrees of freedom and making sure that the reflections on either surface of the lens were coincident on the surface of the laser over here. After that was set up, we know that there's a beam waist that is converging somewhere here because we are inducing a positive lens. So what's happening is the laser is converging here to a point somewhere, and we're using the microscope to find the focus of the beam waist, the smallest point. So normally we would use a shear plate, but we can see over here that we actually have visible fringes. So we shouldn't really be able to see those right now. So fortunately, we can kind of guesstimate where our spot size is supposed to be by translating our microscope down. So as you can see, our spot is getting a little bit larger. So we know that we're not actually at the focus of the beam waist. And if we move it too far forward, same thing happens. So it's gonna be somewhere in between when our spot size is the smallest, which is around here. So considering that we have our secondary beam waist here, we are measuring at points beyond and behind on the optical axis using the same razor blade method that we did in the first part of the lab. So by scanning across the knife and recording our values on our transimpedance amplifier, we can use that to determine the radius of the beam at various locations that we record. Using these locations, we can find the exact size of or calculated size of the beam waist, and also the Rayleigh range for the secondary beam. For our post-lab processing, we needed to plot the power readings we found in lab as a function of the knife edge position. In class, we defined the beam radius as the region of the beam that contains 16 to 84% of the power curve when scanning the knife edge across it. So, when using the data we collected, the beam radius was defined to be the region of 16 to 84% of the normalized power readings we found. By putting our data set into Excel, we were able to see a similar power trend to what was viewed in class. In our first setup, we found that 16 to 18% of the power region corresponded to 240 microns of knife translation at one axial location, Z1, and that at Z2, the knife translation distance was 300 microns. This Z2 was located 1,200 millimeters away from Z1, which is exactly our delta Z value. By inputting these values into our MATLAB code used for the pre-lab, we could solve for all the necessary quantities.
Using our classical beam profiling algorithm, the beam waist of the HENI was calculated to be 167 microns, and the beam waist location was calculated to be in front of the laser cavity. However, the beam waist should be located inside of the cavity. For the second part of the lab, we placed the lens in the system to create a secondary beam waist. During our calculations, however, we found the beam waist diameter being complex numbers. We concluded that our main source of error comes from our photodiode not being placed directly behind the knife edge. Instead, it was placed about 10 millimeters behind. This was the closest we were able to get the photodiode to the knife edge due to the mount the knife was placed in.